Hello everyone. In this session, we're going to talk about IC technology from a VLSI perspective. This session will be like an overview to VLSI, sort of like scratching the surface, as we say. See, all of us have grown up in the information age, right? We have seen technology change from year to year. We have seen phones becoming smaller, and we have seen computers becoming faster and faster, right? So when you think of the phone like 20 years back or 10 years back, how was your phone? How was the computer like? It's totally different from what you have now, right? So what is driving this change, or what is enabling this change? It's VLSI, right? VLSI is very large scale integration technology. We are all digitally connected like never before using this, right? In such a short time. So I'm presenting this session with the hope that this will further your understanding of VLSI industry. Like if you're already have gone through a course in your academics, or you might be having some knowledge of this technology. So this, I hope, will further your understanding. And I also hope that you will be able to identify certain areas, and you can also identify some career opportunities. The agenda of this session I divided into 8 parts. So we'll be starting with the introduction of VLSI, and then we'll look at the different stages which are present in the VLSI flow. And then we'll look at the important skills which are required which are usually in demand in the VLSI industry. Then we'll look at an example of a tool or a Verilog simulation. Then we'll look at 2 case studies. And with these 2 case studies, we'll be getting some understanding of what kind of work that happens in the industry. Then we'll look at certain current trends, like what kind of new things that are happening in the industry, or what is driving the VLSI industry. Then followed by that, you'll be able to get some idea of the different kind of career path and job opportunities that are available in the industry. All right, so what is VLSI? So VLSI has a history, right? So it started with integrated circuits. So what is an integrated circuit is mainly nothing but many set of transistors in one chip. And when it comes to VLSI, it's millions. It's usually millions, or it can be billions of transistors in a very small area. So what are all the different objectives of IC technology? So if you look at the history, right? If you look at the picture on your right, there's a hard disk from the year 1956. So this hard disk had to be taken in a truck, or if you want to transport it to one place to another, and it had only 5 MB of capacity. And when you look at the second picture, it is a 1 terabyte of memory card, and this was recently designed. It is available in the market, and this can fit in your fingertip. So this kind of change has been possible because the objectives in IC technology were to reduce the size of the device or the transistors, and also to reduce the power, and to make at the same time to make the chip or the hardware very fast and increase the performance of this hardware. When it comes to VLSI, so there are certain terminologies that are used in VLSI. So the IC fabrication technology progresses from one process node to another process node. So each process node is denoted by the smallest element in the transistor, or the size and length of the gate, which is usually in nanometers. It can be 22 nanometer, 14 nanometer, 10 nanometer, and so on. So as the technology advances, the size of the gate also reduces, right? So right now there are, in 2020, the process node is around at 7 nanometer, 10 and 5 nanometer. So going forward another 2 to 5 years, it will reach up to 2 nanometers. So the question is, what will happen when the limit is reached? So what will be the challenges, or what are the challenges that are being faced right now in the industry? Of course, there's a limit to which the size of the gate's length can be reduced. Research is currently going on what can be done, but there's a lot of potential with the existing technology. The demand for the current technology continues to remain strong, and the complexity with the existing technology is a lot. In fact, it can support a lot of things with a lot of applications with the existing technology. And there have been ways that have been found to achieve high performance and low power consumption with the same size. People have found ways to do stacking one transistor on top of another, and there have been ways that have been found to deal with such challenges. Next, we'll look at the different stages in the VLSI technology. So I have listed down 7 stages. In the industry, there can be more, or there can be different kind of flows, but the idea remains the same, that you start with the specification and then ultimately create some kind of a layout, and then that is given to the fabrication or the manufacturing or the fabrication facility. Let's look at these stages one by one. First stage of the VLSI flow is the chip design specification. So this involves mainly defining the features in this specification of the system. Let's say you want to design, or you want to manufacture, or you want to build a smartphone. What are all the different features you want to support? These features can be what is the camera you want to support, or what is the sensor, what kind of fingerprint sensor you want to support, or what kind of processor you want to support. All these becomes the spec or the features of the system. And then you kind of come up with the high level representation of the system, and you need to consider the performance area, what kind of fabrication technology which you want to use ultimately. Based on this, you kind of get a broad understanding of the product which you want to build. The next step in the VLSI design flow is the architectural design. So in the next step, basically what happens is that a basic architecture of the system is created, and certain decisions are made on the instruction set, cache size, and other aspects. These are mostly related to the processor. Let's say you are using an ARM kind of a processor. There are certain decisions which you have to make, what kind of memory internally it has, and what kind of cache you want to store. After making those kind of decisions, you create a architectural specification. This is a lower level kind of a document where you specify in detail what kind of decisions you have made, and what kind of features again you are supporting, and how the design should behave. And you can see in the diagram on the right, it basically shows a kind of a block diagram where the data flow is kind of represented using arrows. It's not completely detailed. It kind of gives the idea to where what needs to be done in the next step. So in the next step, you have to do the behavior and functional modeling. So in this step, you need to define the main functional units of the system, and then you need to specify the timing of each unit. So as you saw in the previous slide, there were different blocks in the system, and there will be a timing for each of those units. And when it comes to a design, timing is very critical. A lot of things can make or break because of the timing. So the timing is exactly kind of defined in this step. And you can see on the right, there are certain waveform kind of diagrams, and these diagrams usually kind of denote what will happen to certain signals which are present inside the design. Certain input or a stimulus is being driven. It also gives a relationship between different kind of blocks. The next step in the flow is the logical implementation. So until now, you were kind of specifying, you are deciding the features, and you are deciding how the blocks will behave conceptually. Now, from this step onwards, the actual design work begins. So in this step, you need to describe the logic and the control flow in the form of a RTL, or register transfer logic. So there are usually in the industry, how it works is this RTL is represented using a HTL, which is nothing but a hardware definition or a description language. And the examples of this HTL is Verilog or VHTL. And there are new languages which are also being supported, but across the industry, Verilog and VHTL will be the mostly used set of hardware definition languages. Using Verilog, you can describe the RTL or the logic using a kind of a behavioral code. It can also give you an understanding how the design will behave. And once the hardware is defined using the HTL, you can also test and verify it. On your right, you can see a diagram. So you can see there is a set of code, and there is a representation of that code in the form of a schematic. So basically, this code which you can see on your right is nothing but it's representing a D flip-flop. We will look at how this happens in a later in the example. Okay. So the next step after you define your HDL, your RTL using the HDL, is the synthesis and testing part. So in this part, in this step, what happens is that the design, which is in the form of an HDL, gets represented in the form of a circuit or a netlist. So there are different elements which can be transistors or wires or cells, standard cells and those. The design of the HDL gets converted into this by using some, usually kind of a software which understands that HDL code and gives you this circuit representation. This again has to be verified or has to be checked to if it matches with the intended purpose or if it is actually working as expected. And there is something more or less gate level simulation to do that. The next step in the VLSI process is the PN or the placement and routing. So until now you had the circuit representation or you had the logical representation, and this has to be converted into a geometric representation or nothing but the layout. So again, this conversion is facilitated by a tool, or usually you give the circuit representation or the gate level or the netlist to certain tools, and they will basically create a layout out of that. Further, you need to do floor planning, which is nothing but placing the different blocks which have been generated by the tool and relative to each other, so that you can optimize the power and you can best reduce the area. You have to again need the timing using the help of clock tree synthesis. Then routing has to be done for different blocks and you need to determine the actual delays. So all of these steps which I am listed down can be different stages altogether, and these happen. There are different individuals which only focus on certain parts of the stages. Again, it depends on company to company. Industries interchange these steps, the order of these steps. So at the end of the objective of the stage is to basically create a layout out of your design. Then coming to the final stage, in this stage, once the layout is generated or created, you need to verify that physical layout. There are different ways, there are different steps to verify that layout. You compare with the schematic, layout versus schematic, and then you check the design using, there are certain rules which have to be met. You have a DRC or the design rule check for that, and you need to also ensure that layout is equivalent to the intended logic which you had initially written. After ensuring all the checks are passing and once you get considerable confidence on the layout, you need to create the GDS file, or the GDS file gets generated. This is a standard format which is used across the industry for the fabrication purpose. This file gets sent to the fabrication, and the fabrication plant or the fabrication unit will basically generate a wafer. Wafer is nothing but it's a combination or a set of ICs or the chips which gets produced, and these chips are again cut out and they're packaged and they're ready for testing. Ultimately, these ICs get packaged and then they are again further tested and they are ready to be used by the end customers. So this was a brief set of stages which I had explained, covers the VLSI flow. Again, apart from these, there are certain stages which are happening in parallel, like there is design for testing, which is designing the logic or the hardware which is focused on the testing of design or the hardware. So you need some kind of access to the IC once the IC is ready, and design for test or design which is focused on the debugging part will give you that access once the IC is ready, and you will know what is happening exactly inside the design if when you go for DFT. Apart from DFT, there is also some kind of software or middleware work that happens. So when your design gets until your design gets manufactured, There will be a software team who will work on the creating drivers and softwares. And once you have the chip ready, you can dump those software files and you can test them. There's also some kind of prototyping that happens using FPGAs. We'll talk about that in another slide. So what kind of skills are required if you want to be part of VLSI industry, or we can say that what kind of skills are necessary? So the basic is the logic and electronic design, or basic electronics. Apart from the knowledge or the understanding which is present in the academics, there is some advanced level of basic understanding, and also the advanced level of logic and electronics and design understanding is required when it comes to VLSI. The second one is the hardware definition language. As I mentioned in one of the stages, hardware definition language can be Verilog or VHDL. The idea is that the candidate or the engineer should know how to write HDL codes and how to conceptualize the design. Then it's programming and scripting languages. A lot of flow in VLSI industry is highly automated. There's scripting languages like Python, Perl, which is to automate the flows in VLSI. And programming is another aspect. Programming, when I say programming, the object-oriented programming, which all of you must have a basic understanding of. So that helps with writing good, understandable code, and then reusable code is important in VLSI industry. Then comes the standard methodologies and processes. So VLSI is a vast industry, right? So we are dealing with very complex designs, and there has to be certain kind of standards which has to be followed, like how the HDL code is shared and how team works in a complex project. They are all specified using a standard, and there are standard practices of how a process or how HDL is designed. There are standards mentioned for that. Unified verification methodology is one such standard. Then next is the protocols and technologies. Protocols are standards, again, usually protocols for data transfers, like for example Ethernet and USB. So there are many such data protocols, data transfer protocols, which have to be understood by the professional in VLSI. And apart from this, you should also know EDA technologies. EDA is nothing but electronic design automation tools. And there are softwares. Softwares are extensively used in VLSI. Softwares help automate the process, and they also do a lot of. They simplify a lot of complex processes. Since it is impossible to create such complex designs with manual connections, a lot of it is automated using software. So software or the EDA knowledge is extensively used in VLSI.